Hello everyone. Very good morning to everyone. Welcome to Sai Tutorials Jamkandi. Here 10th class Kannada medium math science English and 10th class English medium math science regular classes as well as online classes are available. Please join us and learn more. So dear students, in previous session we have discussed the second PUC physics chapters, that is first chapter electric charges and fields. So in today's session, I'm going to start the introduction part related to the electrostatic, potential and capacitance. So here the two concepts are present. One is electrostatic potential and capacitance. Okay. Two concepts, electrostatic potential and capacitance are there. So let us learn one by one. What is electrostatic potential and capacitance? What are the phenomena present in the electrostatic potential and capacitance? See, the first and foremost concept related to your syllabus, that is, what do you mean by electrostatic potential? Okay, what is electrostatic potential? See, what is the definition is electrostatic. This is all the phenomenon related to electrostatic. So it is a potential energy possessed by a unit positive charge. See, it is a potential energy. What do you mean by potential energy? You know it very well. Okay. It is related to the position. Okay. It is a potential energy possessed by a unit positive charge at the given point in an electric field and is measured by the amount of work. Okay. Amount of work done in a moving unit positive charge from infinity to that given point against the field. So it is a scalar quantity and it is measured in volt. Suppose, see, electrostatic potential at a point in an electric field is defined as the amount of work done in bringing a unit positive charge from infinity to that point against the electric field. See, suppose if I consider the electric field. Okay, this is the electric field. Let us consider this is unit positive charge A and this is another charge B. Okay, having the point. So this is charge Q1 and this is charge Q2. So electric field is present in this. Okay. So electric potential. Now electric potential at a point P. Let us consider a point P here. Okay. So I have said you that the electric charge, okay, the electric charge will always move from positive charge to the negative charge. See, it is a potential energy. So suppose if I want this point charge to move in this direction, but electric potential at a point in an electric field is defined as the amount of work done in bringing a unit positive charge from here. Let us consider the point P. Okay, having the charge Q0. Now, suppose the work done in bringing a unit positive charge. Okay, work done in bringing a unit positive charge from infinity. Okay, this is, so these lines are in infinity. These lines are up to infinity. Work done in bringing a unit positive charge from infinity to that point against the electric field. Suppose if I consider the point P here, having the charge Q. The work done, okay, I need some work done to move this point charge from infinity to the given point, but this electric field will be opposite to the direction of electric field, against the direction of electric field. So it is called as electrostatic potential. This is called as electrostatic potential. See, electric potential at a point in an electric field is defined as the amount of work done, that is denoted by W. Am I right or not? Okay. The work done in bringing a unit positive charge. Okay, this is maybe a unit positive charge from infinity to that point against the electric field. So that against the electric field, such a work done is called as the electrostatic potential, that is denoted as V. Okay, it is a scalar quantity. It is a scalar quantity. So it is can be denoted as so it is a potential energy possessed by a unit positive charge at a given point in an electric field is measured by the amount of work done in moving a unit positive charge from infinity to that given point against the field. It is a scalar quantity. It is a scalar quantity and is measured in volt. Suppose that is it is denoted electrostatic potential is denoted by the letter V. Okay, is equal to from infinity to that point. Suppose if I take that point as R, then it is from infinity to that point R having the charge Q naught, having the charge, suppose it may be any charge that is negative or positive charge. So this is a negative. Okay, negative. Why it is negative? Because that point charge is moving against the electrostatic field. Am I right or not? So that's why I have written minus here. So from infinity to that point, the total work done is equal to a unit positive charge from infinity to that point to the given point against the field, that is electrostatic field, E bar into dr bar. This is the expression for electrostatic potential. This is the expression for electrostatic potential. See, it is a potential energy. It is a potential energy by a unit positive charge at any given point in an electric field and is measured by the amount of work done in moving a unit positive charge from infinity to that point given R is equal to the given point against the field. Okay, given point against the field. Why it is negative here? Because that electric field is moving against the point charge. Okay, it is a scalar quantity and it is measured in volt. This is very important. Electrostatic potential is, the SI unit of electric potential is volt. Now, the electric potential at a distance r from the charge q is given by, okay. Suppose if we continue, if we go on deriving this expression, we will get that q divided by r. See, suppose let me derive this expression. I have said you that let us consider an electric field. Okay, let us consider an electric field. This is also infinity. This is also infinity. Suppose this is point A and this is point B and it is a unit positive charge at a point P. Okay. So, and electric potential V at a distance R. Okay, they have said that the distance will be the total distance from this point to from this point. It is R. But this small distance of two charges will be dr. small distance it is. Okay, this is small distance. Now the small work done for bringing the unit positive charge from A to B. This is dr. Now the work done W can be written as the work done dW for that point charge A to B is equal to F into dr. Okay, F into dr bar. Suppose here it in the degree, that is 180 degree. Okay, this is cos into cos, just a second, or it can be written as dW is equal to F into dr into cos 180 degree. Am I right or not? Okay, it is cos 180 degree. But what is cos 180 degree? That is minus 1. So that equation will become minus F into dr. F into dr. So where F is, what is the force? F is 1 divided by 4 pi epsilon naught into at a point charge, let us consider that is Q. So it is Q divided by x square. Another charge, that is point charge 1. Unit positive charge, that is plus 1. So Q into 1, Q. So into x square or R square. Okay, it is R square. Now the work done, total work done for bringing the unit positive charge from infinity to point P. Okay, from infinity to point P. This is equation number 1. Okay, this is equation number 1. Suppose if you put this equation in equation number 1, the work done will become minus 1 divided by 4 pi epsilon naught into Q divided by R square into dr. This is equation number 2. Okay, this is equation number 2. Now the total work done for bringing the unit positive charge from infinity to point P. Okay, from infinity to point P, that work done, the total work done will be denoted as, just a second. Now the total work done, okay, the total work done from bringing the unit positive charge from infinity to point P, that is W is equal to infinity to point P. Suppose from infinity to point P, that is minus, same here, 1 divided by 4 pi epsilon naught into Q divided by R square into dr. Okay. So suppose if you go on substituting here, Q 1 divided by 4 pi epsilon naught and Q are common here. So I will take these two terms outside. Then W will becomes minus 1 divided by 4 pi epsilon naught into Q integration of infinity to R into 1 divided by R square into dr. Okay. So integration of 1 divided by R square will become a minus 1 by minus, this is minus 1 by R square will common. So integration of minus 1 divided by R square will become minus 1 divided by R. So if you put the values, that is infinity to R, it will become 1 divided by R minus 1 divided by infinity. So 1 divided by infinity will be going to 0. Then the equation will become electric potential. The total work done in bringing the unit positive charge from that point, from infinity to that point, will becomes 1 divided by 4 pi epsilon naught into that charge Q divided by R. This is the expression. Is it not? This is the expression. This is called the total work done is called electric potential at a point P. I hope this concept is clear to you. Okay. The electric potential V at a distance R from a charge Q is given by V is equal to 1 divided by epsilon naught into Q divided by R. They have taken Q as a unit positive charge and I have taken capital Q as unit positive charge. There is nothing difference here. Okay. So let us move to the next concept. Okay. Suppose if next concept, that is if capital U is a charge in a change, I mean change in potential energy. Sorry, the change in potential energy of a system on a charge Q move through a distance against an electric field E, then that change in potential energy will become minus Q E D. How it will become? See, the change in potential energy of a system on a charge. Suppose if you consider any system, it is having some kind of charges plus Q or minus Q like this. So through a distance, okay, through a distance against an electric field, then that change in potential energy will become minus Q into dd. That's how I have shown in the figure. Okay, that's how that I have shown in the figure. Suppose it is A at a point charge A, it is A at a point charge Q1 and it is B at a point charge Q2, and suppose if you consider at a point that is capital Q. So the change in potential energy of a system on a charge Q moves through a distance. It is having some kind of distance, that is d, the against an electric field. Then the change in potential energy will become minus Q into Ed. Okay, minus Q into Ed. The electricity potential at a point V will become delta U divided by Q. Okay, electrostatic potential at a point. This can be written as delta U, the change in potential energy per unit charge. This is the electrostatic potential. Electrostatic potential. These points to be remembered. The one is electrostatic definition, what is electrostatic potential, whether it is scalar quantity or vector quantity, and the SI unit of electrostatic potential, and the electric potential V at a distance from a charge Q is given by V is equal to, it is denoted by the letter V is equal to 1 divided by 4 pi epsilon naught into Q divided by R. Suppose if del U is a change in potential energy of a system on a charge Q move through a distance against an electric field E, then del U will become minus Q into ED. Electrostatic potential at a point is V is given by del U divided by Q. That is, the potential energy per unit positive charge at a point in an electric field is called electrostatic potential at that point. This is the definition for electrostatic potential. The potential energy per unit positive charge at a point in an electric field is called electric potential at that point. Okay. So that electric potential due to a point charge, I have derived this is equal to 1 divided by 4 pi epsilon naught into Q divided by R. This is the expression for electric potential due to a point charge, that is equal to 1 divided by 4 pi epsilon naught into Q divided by R. Now the potential due to a charged spherical conductor is, that is I have derived 1 divided by 4 pi epsilon naught into due to a charged spherical conductor. See, suppose if you consider the potential due to a charged spherical conductor, see this is a spherical conductor, it is having some kind of positive charges over there. If we consider the point charge P at a point outside the surface, okay, outside the surface, then okay, in the first chapter I have considered an area like this, I mean the unit positive charge. Suppose this is a spherical conductor, okay, this is a spherical conductor, it is having the origin O and distance R. Okay, distance R, and which is having the charges plus Q. Some kind of charge plus Q. Now at a point P, which is having the distance from origin, that is capital R. At a point P, ds having the surface ds bar, electric field E bar. Now to derive the electric potential, I have considered at a point outside the electric field, I mean outside the conductor, then the small r becomes greater than r. Small r becomes greater than r. Then if you consider V is equal to, what is the formula for V? That is minus integration of E bar into dr bar. Okay. Dr bar. If you go on substitute this equation, we will get See, if you go on substituting here, E is equal to 1 divided by epsilon naught into R. Another one R it is present, that is going to be R square. Now V is equal to 1 divided by, see, if you substitute, V will becomes minus, Q is also common here, and 4 pi epsilon naught is also common. So for a point infinity to that point R will becomes, what is R square? Integration of 1 divided by R square, it is minus R. Okay, if you substitute minus infinity to that point R is equal to, what is minus into minus? Plus. So the equation will become 1 divided by 4 pi epsilon naught into that point charge Q divided by R. Isn't it? This is the expression for potential due to a spherical conductor, that is, I have considered the point charge Q divided by 4 pi epsilon naught into R. They have considered X, but I have considered R here for a point on the surface or inside the, suppose if you consider the outside the spherical shell, it is Q divided by 4 pi epsilon naught into R. Inside the conductor, it is capital R. Okay, for it is the distance from unit positive charge at a origin to that point P, it is outside the point, it is this thing. Okay, for a point on the surface or inside the conductor, the potential will be Q divided by 4 pi epsilon naught into R, where that is from at point O to at a point, the distance R. Okay, this is the expression for potential energy per unit positive charge at a point in an electric field. Okay, this is the electric potential due to a spherical conductor. Okay, see, let me tell you, let me revise you. See, it is a spherical conductor. Okay, let me rub these all things. Suppose if you consider the unit positive charge, the distance from spherical shell, okay, this is a charged spherical conductor that is having the unit charge Q, okay, having the positive charges Q, from origin to that distance, the distance from origin to that point is R, okay, that is small r. Okay, now at a point, suppose if you consider the point P anywhere in the, okay, let us consider this is point P. So what is the condition? The potential due to a charged spherical conductor outside the surface, okay, outside the surface of at a point outside the spherical conductor, then in this phenomenon it is having the distance, okay, it is having the distance x they have considered. In that condition, what will happen? X is the distance of the point from the center of a charged sphere. Now for a point on the surface, okay, the point charge due to spherical conductor outside the spherical conductor, it will become capital Q divided by 1 by 4 pi epsilon naught into x. Okay, this is x. Suppose for a point on the surface or inside the conductor, this for this part only, don't consider this point. For a point on the surface or inside the conductor, the potential is Q divided by 4 pi epsilon naught into R, because that small distance R is greater than X. Okay, greater than x in that condition. That's why it is equal to q divided by 4 pi epsilon naught into r. So for points on the surface or inside the conductor, the potential will be like this. So dear students, I hope this session is clear to you. A very introduction part I have discussed today, that is electrostatic potential. What do we mean by electrostatic potential? Whether it is scalar quantity or vector quantity, and it is the SI unit of electrostatic potential and how it will be denoted and what is the formula related to it, and the electric potential V at a distance r from a charge q, how it will be derived I have said you, and if and what is unit positive, what is change in potential energy, and what is the formula. Electric potential at a point V, how it will be derived, that is unit positive charge, that is potential energy per unit positive charge at a point in an electric field is called as potential, electric potential at that point. Okay, suppose if you consider how it will be denoted, potential due to a point charge, that is 1 divided by 4 pi epsilon naught into q divided by r. And potential energy, okay, potential due to a charged spherical conductor. For a spherical conductor, how it will be derived, we have seen here, where x is the distance of the point from the center of the charged sphere. For a point on the surface or inside the conductor, the potential will be like this. So in the next concept, we go on understanding the concept related to electrostatic potential. So these are all the phenomena I have discussed today. So introduction part is over. I hope this session is very helpful to you. Okay. So by this concept, I am going to wind up the session for the today's session. So I hope it will be useful to you people. And thank you, and please don't forget to subscribe our channel. Have a good day.